The first step in match manufacturing involves selecting and preparing the raw material, usually softwood, such as aspen or pine. The logs are debarked and passed through a rotary peeler, which converts them into thin veneers. These veneers are then chopped into uniform matchstick-sized splints using precision cutters. Ensuring uniform size and shape is crucial for further processing. Once the splints are chopped, they undergo a thorough cleaning process. This involves removing any dust, wood shavings, or unwanted particles using water and mechanical sieving techniques. To enhance the performance and durability of the matchsticks, the splints are treated in this phase. They are first soaked in a chemical solution that removes any remaining impurities. After cleaning, they undergo carbonization, a process in which the lower end of the splint is slightly burnt. This treatment prevents the matchstick from smoldering after ignition and improves combustion control. The branding and labeling process begins at this stage. Printing is done on the matchbox packaging material, where company logos, safety instructions, and other relevant details are applied using high-speed printing machines. This step is essential for brand identity and marketing. To protect the printed matchbox material from moisture and wear, a thin plastic or wax coating is applied. One of the critical components of a matchbox is the striking surface. A special friction material, typically made of red phosphorus, powdered glass, and adhesives, is applied to the side of the outer matchbox. This surface plays a vital role in igniting the matchstick when struck against it. Quality control is an integral part of match production. In the laboratory, match samples undergo various tests to check for ignition reliability, burn time, safety, and chemical composition. Ensuring that matches ignite consistently and do not pose fire hazards is crucial before they reach consumers. The outer box, which houses the matches, is manufactured using cardboard or thin wooden sheets. The pre-printed and laminated sheets are cut into the required sizes, folded, and glued to form the final outer box structure. The inner tray, which holds the matchsticks, is also made from cardboard or wood veneer. These trays are cut, folded, and glued into shape before being inserted into the pre-made outer box. The design ensures that matches remain securely in place while allowing easy access for the user. This is the most crucial stage in matchstick production. The splints are dipped into a chemical solution containing oxidizing agents, binders, and combustible materials. The primary ingredients include potassium chlorate, sulfur, and glue. After dipping, the coated splints are dried in a controlled environment to ensure proper adhesion and stability of the chemical coating. The final stage in match manufacturing is packaging. The chemically treated and dried matchsticks are placed inside the inner box, which is then inserted into the outer box. The packed matchboxes are checked for quality, sealed, and arranged in cartons for distribution. Proper packaging ensures that the matches remain safe, dry, and ready for use. Each of these steps is executed to produce high-quality, safe, and reliable matches. The combination of advanced machinery, quality control, and careful handling ensures that the final product meets industry standards and consumer expectations. The process begins with raw wood materials being fed into a wood chipper. The wood chipper reduces large pieces of wood into small chips of uniform size. This ensures that the final product has a consistent texture and density. Once the wood chips are prepared, they are sent to a dryer to remove excess moisture. The moisture content must be reduced to a required level to ensure proper bonding with adhesives in the later stages. This drying process is essential for maintaining the quality and durability of the particle board. After drying, the wood chips are screened to separate them into two different sizes: fine particles and coarse particles. Fine particles are used for the top and bottom layers of the board, while the core consists of coarser chips. This three-layer structure enhances the strength and surface smoothness of the final product. In this step, a quality adhesive, typically a resin-based glue, is added to the wood chips. This ensures proper bonding and durability. The glue-coated chips are then transferred to the forming stage. The glue-coated wood chips are arranged into a mat according to the desired thickness and density of the particle board. The fine particles form the top and bottom surfaces, while the coarse chips make up the core. The formed mat is pre-pressed to give it initial strength and stability. This step also ensures that air pockets are removed before the final pressing. The pre-pressed mat is then cut to the required length using a mat cutter. The mat is subjected to high temperature and pressure in a hot press. This process activates the adhesive, bonding the wood particles together to form a solid board. The pressing time, temperature, and pressure are carefully controlled to achieve the desired strength and density. Standard particle board. A general-purpose board with a sanded surface, often used for furniture and construction. After pressing, the rough edges of the board are trimmed to the final required dimensions. This step ensures uniformity in size and improves the overall appearance of the particle board. Flooring-grade particle board, specially manufactured for use as a subfloor material due to its higher density and strength. To achieve a smooth surface, the board is calibrated and sanded using a sanding machine. This step removes any imperfections and prepares the board for further finishing, such as lamination or painting. For decorative particle boards, a printed paper layer impregnated with melamine resin is applied. This process enhances the appearance and adds a protective layer to the board. The impregnated design is then bonded to the surface using a pre-lamination press, ensuring a durable and aesthetically appealing finish. The production process of birch plywood begins with the careful selection of birch logs, which are peeled into thin veneers. These veneers are dried, sorted, and layered with alternating grain directions to enhance strength and stability. The layers are then bonded using high-pressure and heat-pressing techniques, ensuring a robust and reliable final product. The result is a plywood sheet with excellent structural integrity, resistance to warping, and a uniform surface ideal for further finishing. Bayou, a leading supplier in the industry, ensures that its birch plywood products meet the highest standards. With strategic partnerships with top manufacturers and a strong supply chain network, Bayou provides high-quality plywood in various dimensions to suit different customer needs. The company also prioritizes sustainability, offering FSC and PEFC certified products that comply with environmental regulations. Applications of birch plywood's versatility makes it suitable for a wide range of applications. Construction, used in formwork, flooring, roofing, and wall panels, due to its high load-bearing capacity and moisture resistance. Furniture manufacturing, preferred for cabinets, tables, chairs, and decorative panels thanks to its smooth finish and ease of machining. Automotive and transportation, applied in-vehicle flooring, trailer linings, and cargo containers due to its lightweight yet durable nature. Packaging, utilized for crates and industrial packaging where strength and impact resistance are crucial. Interior design, commonly used for wall cladding, ceilings, and aesthetic applications in residential and commercial spaces. With a commitment to quality, timely delivery, and customer satisfaction, Bayou continues to be a trusted supplier of birch plywood, catering to the growing demand in Turkey and international markets. Birch plywood is a high-quality engineered wood product made from multiple layers of birch veneer, bonded together with strong adhesives. Known for its durability, strength, and smooth surface, birch plywood is widely used in various industries, including construction, furniture, automotive, and packaging. The straw house is an experimental eco-home built in 1998 as Denmark's first house with exterior walls made entirely of straw bales. With a total floor area of 225 square meters, including a converted attic, it was constructed as part of 4 intensive 14-day courses on straw building techniques. The house drew inspiration from sustainable construction practices in the United States and France, and aimed to explore the potential of straw as a natural, energy-efficient building material. The straw house was designed with a strong emphasis on sustainability and resource efficiency. The key materials used include straw bale walls. The 60 centimeters thick straw bales provide excellent insulation, reducing the need for additional heating. Recycled concrete. The foundation was made using crushed recycled materials, minimizing waste. Floor insulation. A combination of mussel shells and polystyrene was used to ensure thermal efficiency. Clay and brick interior walls. The inner walls were constructed from reclaimed bricks and unfired clay bricks, contributing to natural humidity regulation. Wooden structure. The timber frame was built using debarked tree trunks sourced from Dover Forest. Flax roof insulation. The house used flax fibers instead of conventional insulation materials. The straw house was designed to be completely self-sufficient, operating without any connection to the electrical grid or telephone lines. Its energy system included wind power, a 2.2 kilowatts. Proven wind turbine provided the house's electricity. Battery storage. A 2000 Ah battery system stored excess energy for continuous power supply. Heating system. A wood-fired boiler supplied central heating through underfloor heating pipes. The house featured a heat recovery system and a 1,000-liter hot water storage tank to improve energy efficiency. Advantages of straw bale construction. Straw bale homes offer several environmental and practical benefits. Improved indoor climate. The breathable walls and clay plaster help regulate humidity, reducing the risk of mold, and ensuring a healthier living space. Energy efficiency. The thick straw walls retain heat in winter and keep the interior cool in summer. Sustainable materials. Straw is a locally available renewable resource that requires minimal processing and energy. Despite its many advantages, the straw house also highlighted some challenges of straw bale construction in Denmark. Moisture issues. The south and west-facing walls absorbed moisture from wind-driven rain, leading to concerns about long-term durability. Without proper protection and ventilation, straw walls can struggle to dry out, potentially affecting the structure's lifespan. The process begins with logs being transported to the plant by contracted log haulers. Upon arrival, they are unloaded into the log yard using a button-top grapple machine or a 966 cat loader. The logs are then carefully sorted and transferred to the bucking station. At the bucking station, logs are measured and cut into the appropriate lengths needed for further processing. The movement of logs at this stage is controlled by a sophisticated computerized system, reducing the need for manual intervention and increasing efficiency. This automation ensures precise log cutting, minimizing waste, and optimizing material usage. Once the logs are cut, they are placed onto a conveyor system that transports them toward the debarking station. During this transfer, the logs are automatically positioned and fed into the debarker to remove their bark, preparing them for the next stage of the process. The integration of automation and efficient handling at this stage ensures a seamless transition from raw logs to processed veneer-ready material. The debarker is equipped with 5 arms fitted with sharp teeth that efficiently remove the bark from the logs. Once the logs exit the debarker, they are transferred onto the slasher deck, where saws trim them into uniform 8-foot pieces, now referred to as peelers. These peelers are then scanned to determine their diameter and length before being directed to the appropriate bins. The peelers are then scooped up by loaders and placed into one of 10 vats, where they undergo a 12-hour hot water shower. This soaking process softens the wood, making it easier to peel into thin veneer sheets in the lathe. One loader is responsible for filling the vats, while another empties them and prepares the logs for the next stage. Once softened, the peelers are fed into the roundup lathe to remove any remaining bark and prepare them for the spinless lathe. The logs are then transferred via a jack ladder to the spinless lathe, where they are peeled into long, thin veneer ribbons of approximately 1/8 inch thickness. These ribbons are carried by trays to the clipper, which cuts them into standard 4 by 8-foot sheets. The clipper system also detects defects and sorts veneers based on moisture content. The veneer sheets are categorized into different moisture sorts: heavy sap, highest moisture content, sap, light sap, and heartwood. They are then sent through a dryer, which operates at an average temperature of 400 degrees Fahrenheit. The drying process takes approximately 3.5 minutes per sheet. Once dried, the veneers pass through the MetroGuard system to measure their density and strength. Another scanner checks for moisture content, to determine whether the sheets qualify for LVL production or should be sent to the Alberta Plywood plant. The sorted veneer sheets are arranged into stacks based on a predetermined recipe, which varies depending on the grade or strength of the LVL being manufactured. The veneer sheets are then run through a glue curtain that evenly coats all sheets except for the top face. Following this, the sheets move to the layup area, where they are overlapped and aligned before entering the continuous press. As the veneer stack enters the press, it passes through 3 10-kilowatt microwaves that heat the glue to bond the sheets together. The press applies a hydraulic pressure of 300 pounds per square inch to compress the layers to the correct thickness. The LVL boards are then cut into lengths ranging from 20 to 60 feet, depending on customer specifications. The press has an annual production capacity of approximately 3.6 million cubic meters of LVL. The cured LVL boards are transferred to the beam and header area using a crane capable of lifting 20 tons. The boards are then fed into the gang saw, which cuts them into specified widths. The grading deck operator inspects the boards for defects, separating the good boards from the defective ones. Any boards with imperfections are trimmed to a usable length. The boards then pass through a wax box that coats the cut edges to prevent moisture absorption. At this stage, an automatic grade stamp is applied. The final step involves stacking and preparing the LVL boards for shipment. The strapping operator measures and trims the boards to the correct length before wrapping and labeling each package with product specifications, including length, width, and grade. The finished LVL boards are then loaded onto trucks for distribution across Canada and the United States. West Fraser maximizes resource efficiency by ensuring that no part of the log goes to waste. Wood chips generated during the process are used in the pulp industry, while residual bark and wood waste are processed into biomass fuel. Additionally, leftover cores from the peeling process are repurposed in the wine industry as grape stakes. Saw logs are categorized into different grades based on their quality, size, and usability in lumber production. The grading system is crucial in determining the value of each log and how it will be processed in the mill. Veneer logs, these are the highest quality logs, free from knots, cracks, or other defects. They have a straight grain and uniform structure, making them ideal for producing high-end veneer sheets for furniture, cabinetry, and decorative paneling. Veneer logs are sold to specialized buyers who regularly inspect and purchase them from mills. Prime or select logs. These logs are of excellent quality, but may have minor imperfections that prevent them from being classified as veneer logs. They produce high-grade lumber used in flooring, furniture, and architectural millwork. Standard saw logs. This category includes logs with some knots, minor defects, or irregular grain patterns. They are used to produce construction-grade lumber, hardwood flooring, and general wood products. The debarking station is the first step in sawmill processing, where logs pass through rotating drums or cutter heads that strip off the bark. This process removes dirt, grit, and debris, preventing saw blade damage. The extracted bark is repurposed for landscaping mulch, biofuel, or other byproducts, ensuring minimal waste. The saw filing department plays a vital role in ensuring the efficiency, accuracy, and quality of a sawmill's production. Saw filers are responsible for maintaining, sharpening, and repairing all saw blades in the mill. Proper saw maintenance affects mill performance, lumber yield, and the appearance of the final product. Saw filing is both a technical skill and an art, requiring precision and experience. Once logs pass through the debarking and metal detection processes, they are conveyed to the head saw deck and placed on the carriage. Here, technology scans each log to determine its size, shape, and optimal cutting position. Linear positioners adjust the log to maximize yield before the head sawyer begins cutting. The head sawyer removes boards from all 4 sides of the log, shaping it into a square cant that can be further processed. The first cuts remove slab cuts, outer wood with no lumber value, sent to a chipper for byproducts. Jacket boards, higher grade boards sent to the edger for refining. The squared log, cant, then moves to the resaw, while waste materials are processed into wood chips, fiberboard, or energy fuel. This efficient use of materials ensures that nothing goes to waste in the sawmill. The edger is a crucial machine in the sawmill that trims rough-cut boards to remove excess bark, wane, lack of wood, and irregular edges. The edger operator makes real-time decisions to maximize board width and quality. Modern mills use optimizing edgers, which utilize sensors and automation to improve precision and efficiency. The double-end trimmer is a key machine in the sawmill that cuts boards to precise lengths. Positioned after the edger, it trims imperfections from the ends of lumber while ensuring uniform sizing. The operator inspects each board, deciding whether to remove 1 or 2 feet for better appearance and grade. Standard industry trimming leaves boards 2 inches longer than nominal length. Grading is a crucial step in sawmill operations, ensuring that lumber meets industry standards and customer requirements. A skilled lumber grader evaluates each board based on thickness, width, grain quality, knots, defects, and appearance. The National Hardwood Lumber Association, NHLA, sets grading rules for consistency. Higher grade boards are used for furniture and flooring, while lower grades are used for construction or pallets. Modern mills use automated grading systems, but experienced graders remain essential for optimizing value and maintaining mill profitability. The maintenance department is essential for keeping all sawmill machinery operating efficiently. Technicians perform regular inspections, repairs, and preventative maintenance on saws, conveyors, hydraulics, and electrical systems. Quick troubleshooting minimizes downtime, ensuring smooth production. A well-maintained mill improves safety, efficiency, and product quality, reducing costly breakdowns and delays.